So finally, we have to look into different media. So we learned how we can create our signals, what bandwidth, etc. And always I refer to, okay, depending on the physical media. So we have to have a closer look onto what different types of physical media do we have. So all the different media, they vary in their capacity, material, sure, but this is not the topic here in this course, but they vary also in bit error rate, and what is very simple is a twisted pair of copper wires. So insulated copper wires twisted. Why twisting? I come back to this. Then we have coax cable. So coax cable, where you have a conductor and the core that's in the middle, so that's copper, typically copper. You have insulation and you have a braided outer conductor. So that's shown here, coax cable, typically used classical cable TV. Then optical fibers, where you have a glass core and you have some plastic and some other layers. So, and where you transport the light here inside the core, and there are also many differences. Also important, but not the major topic here, radio connections, cellular phones, mobile phones, directed microwave links, and satellite communication. So there are different ways of transmitting our signals. Be aware, we talk about media, different media for satellites. Well, there is vacuum. So we don't need something to transmit electromagnetic waves. But depending on if we use a medium or not, well, wave propagation is a bit different. So if we look at the medium, although sometimes it's not a real medium for in some cases, we can distinguish between guided media and unguided media. So what does it mean? For guided media, we can have a real conductor, copper wires, we'll see, or we can have waveguides. So that means electromagnetic waves are guided inside the medium. And we have unguided. Unguided can be directed and undirected. We'll see examples for this. So let's stay with the guided medium, conductor. This is exactly where we have the twisted pair, copper wire. We see many different versions there. This is what you typically have in local area networks, those installations, and coax cables, the classical cable TV distribution. If you guide the waves, then we have so-called hollow conductors, where you have typically microwaves guided there, or fiber optics. So we guide the waves, the electromagnetic waves, light inside a fiber. For unguided, we can have directed, so this is directional radio, microwave links, for example, or laser to connect different senders and receivers, or unguided, which is then omnidirectional radio if you have an antenna that's not directed, or satellite broadcast, for example, also can be undirected. So you see, depending on the medium, we have different ways of guiding, not guiding, conducting, etc., our electromagnetic waves, or we can simply use an electric current to transmit our data. Okay, so we can classify here the media, and you should roughly know the differences because they all have different behaviors. We come back to some examples here. We can also classify our networks, classify by distance. Well, if we have very small networks around your body, then they are called body or sometimes personal area networks. So in mobile communications, we'll talk about Bluetooth for this examples. We have rooms and buildings, so these are more local area networks, so up to 100 meters, for example. We have campus and towns, metropolitan area networks, wide area networks, if you really cover whole continents, and, well, we have the internet covering the whole planet. There's even an interplanetary internet, so for deep space communications, and there are even IETF standards for this. But what's quite obvious, with the distance, we have an increasing number of users, traffic patterns, and single solutions for one size, one dimension, they do not necessarily scale to others. So we need different technologies when it comes to the medium, but also later for medium access, congestion control, etc., for the different scales. So a solution that fits for local area networks like wireless LAN, for example, absolutely does not fit for wide area networks. No way. And the other way around, maybe a solution for wide area networks is way too inefficient for body area networks. Too much overhead, etc. Okay, we are back to our electromagnetic waves, our signals. So this is what we use. We learned this, we use this to transmit the signal. Wireless, that's quite obvious, but that's not the topic here, but also on cables. So, and we learned in physics, okay, electromagnetic waves, independent of the frequency, they travel at speed of light. Yes, in vacuum, not in, for example, copper or fiber. So rough numbers, only 2/3 of the speed of light. So, and I always said also in the last subsection, well, we can replace wavelength and frequency, and here you see y wavelength times frequency is the speed of light. So that's a very fundamental relationship between wavelength and frequency in vacuum. And this is why we can calculate the length of the wave, one period, at a certain frequency. So it's 3 meters for 100 megahertz, etc. And this has nothing to do with the speed. The speed is always speed of light in vacuum, no matter what the frequency then is. But there are certain properties for certain wavelengths. That's especially important in wireless communication. Okay, fundamental. Now let's look into different media types. So first of all, guided medium. Okay, so that's our simple twisted pair, and there we use electrical signals. So we apply certain voltages, and then actually there's a current that flows through the wire generating magnetic fields, etc. And I'm talking always about twisted pair. We need a pair of copper wires because in the end there's a current flowing from the sender to the receiver and back. With a single wire this doesn't work. You need the loop. So why twisting? Well, the problem is if you have a wire like this and there's a current flowing through the wire, you generate a magnetic field. And this could couple into the next wire. Or if you have interference coming in, then this interference, those fields, those external fields, they can also generate a current causing interference with our data signal. So we can do several things. One, as we will see, is we can shield everything. Well, we'll see how this works. The other thing we can do is twisting. And here you see an example of a cable that contains 4 pairs of twisted pairs. So 8 wires altogether. And the twisting is important to reduce the electromagnetic interference with the environment, and also as we use different twist rates, so how many twists per centimeter, if you look at this blue and white, different twist rate compared to this black and white. So there are less in the black and white and more here, more twists per centimeter or per meter. We reduce so-called crosstalk. Why? Twisting the wires, actually you cancel out the fields. That's the idea. So you don't have these radiating fields from a twisted pair, or at least you reduce it. So that's the core idea. And so it's very simple. It's well known from telephony. You can use this also for analog signals, but here we talk about digital signals and we have certain bit error rates for this. Very, very simple. But be aware, it sounds simple. There are some things you have to take care of. One is the bending radius. So if you have such a cable, never do something like this to bend it too much. There's a so-called bending radius you have to follow, for example, 15 centimeters or whatever bending radius. That means you have to follow this circle with a certain radius here of, for example, 15 centimeters. So if you have real 90-degree corner, you can do this with the cable, but this will, so to speak, de-twist maybe internally the cable, and this makes the whole cable more vulnerable to interference from the outside world. So this is not like a power cable, which you can bend as long as you don't break it. Here, nope, because we transmit higher frequencies, as we'll see. And there are many, many different types of cables here on the left-hand side. You see examples of different cables, and you see here silver shining. Here there's some foil wrapped around it, and there's some braided stuff here and individual foils here. On the right-hand side, you see this magnified a bit more. Here on the lower right-hand side, you see there's a foil, we also call this a shielding around everything, and then an individual shielding. And the more shielding you have, the better you can protect your twisted pair from the influence of the environment. So one important thing is, if we look at different categories, is the shielding. The cheapest one are the so-called unshielded. So if it's unshielded, completely unshielded, that means you do not have these shielding around pairs of wires or around the whole cable. There are different of foil shielding, individual foil shielding, screen shielding, etc. This is not something you have to know in detail, but just to show you that there are many, many differences, and they have their consequences if you have individual shielding, overall shielding or not. And there's a certain notation in industry. So if you have only an individual shield, let's notate it like U unshielded for the overall shield, but it's a foil sheeting for the individual twisted pair. So UFTP means unshielded from the outside, but foil sheeting for all twisted pairs. Or you could have a foil all over plus a foil around each twisted pair. Or you can have screen shielding, braided, etc., etc., etc. What is the idea? Well, depending on the money you want to spend, depending on the data rates you want to achieve, there are different categories of cables. And you can imagine, if you don't want to pay too much, well, you can only have lower data rates. So, for example, classical telephone cables, they can have a bandwidth, now we are back, bandwidth of up to 16 megahertz. And depending on the length, yeah, you can try going up to 100 megabit per second, but well, in typical environments, no, not a good idea. This is why pretty soon Cat5 cables came up, and those Cat5 cables, different subclass, etc., they can at least deliver something like 1 gigabit per second up to 100 meter. So that's something. There are some better cables like Cat6 cables, and they can deliver something like 5 to 10 gigabit per second up to 100 meter. And these are the typical cables. There's also Cat7, never internationally as a standard recognized, but different categories. These are just examples. And these are the cables you will find in a typical installation in buildings. So they have a shielding, an outer shielding, and they have foils wrapped around all individual pairs. So then they are quite robust when it comes to interference, but there are certain maximum cable lengths. Yeah, you can go up to 120 meters depending on the installation interference, and you can still achieve gigabit per second data rates. And then there are special cables, for example, for data centers, you see up to 36 meters. So this is not for larger installations, but if you connect racks in compute centers, then you see you can go with copper wires. So this is not fiber optics, with copper wires up to 40 gigabit per second. That's one of the standards, so 40 gigabit Ethernet, and then you can use these copper wires. We will come to fiber optics. That's complete different game, fiber optics. But here we can go up to this 40 gigabit per second, 40 gigabit, because those cables now offer bandwidth of 2 gigahertz. 2 gigahertz running over twisted pair copper wires for data centers. So that's pretty much. Okay, copper wires, twisted pair. What else do we have? coax cables. So the idea here is we have the copper conductor here, we have an insulation around this, or plastic, and we have an outer conductor here. And these cables, compared to twisted pair, we don't have an electric current flowing through, but we guide electromagnetic waves through these coax cables. So the conductor, yes, it's the core. We have the outer conductor to reduce all the environmental disturbances, and we separate them by insulation. Quite good when it comes to bit error rate, and we have some gigabit per second up to a kilometer, and this is why the cable distribution systems can use this, for example. Yes, fiber is always better, but that's also one way of doing this. Better shielding compared to twisted pair, better signal quality. And early networks, they used this coax cable also for LAN installations. So the first Ethernet installations used coax cable, but today you don't see them anymore. So classical cable networks, they also use this. So if they're there in a building installation, you can use this. But if you do a new installation, you would not use them. So now finally coming to the king or queen of media, guided media, optical fiber. Why? Why in the end, people say it's, well, nearly unlimited data rate. It's not really unlimited, but over long distance, look at these data rates. 2009 already over 7,000 kilometers, 15 terabit per second. Remember, fiber optic, copper wires, we had 36 meters, well, 40 gigabit per second. So that's the most powerful Cat8 cable, 40 gig over 36 meters. And now we're talking about 15.5 terabit over 7,000 kilometers. Then we saw fibers with more than 100 terabit per second, going up to petabit per second. And 22 years ago, there was the first light source to generate light, the impulses fast enough to generate impulses for 1.84 petabit per second. And this is why many people say, okay, unlimited, because with 1.84 petabit per second, we can transmit the worldwide internet traffic over this single light source, at least today. So that's quite a lot. That does not mean that there's a system that can already transmit more than a petabit per second over thousands of kilometers. No. So that's just showing where we can go, and combining this means, well, we have to reduce it. But 15 terabit over 7,000 kilometers, so that gives at least a hope that we will reach this petabit over thousands of kilometers. Why can we do this? Well, we are insensitive to all this interference. That's very good. So because if you shield it, no light goes in, there's no disturbance. Very good signal to noise ratio, great repeater spacing. So to repeat the signals, we'll come back to this in the next chapter. In fiber optics, we can have, for example, every several hundred kilometers, an amplifier that amplifies the weak light pulse and generates a strong one again. And this can be done all optical, so we do not have to retransform this into electrical signal. Very small in size, fibers, quite lightweight. Think of insulation in wherever you have to take care about the weight, then fiber optics is much lighter. But they're also quite sensible when it comes to dust, water, etc. So this is not as simple as one may think to replace all the copper wires in a airplane, for example, by fiber optics. That's a problem. Very low bit error rates. And here we see why we can transmit that many bits per second on this diagram. Here we see the attenuation. That's just an example, giving you several windows where you can transmit data. And here's, for example, at 1550 nanometer, we have an opening, a window where attenuation is quite low. And this means we can use this bandwidth. And if you do the math looking at this bandwidth, then we see, okay, this is why we can have assume very low noise, very good signal to noise ratio. This is why we can have these terabits and petabits, because this is really a big bandwidth compared to the 600 hertz or 200 megahertz, 200 megahertz of copper wires. So optical transmission works as follows. You have an electrical signal, because our computers work with electrical signals, and then we generate somehow the light, we transmit the light, and then we need a detector that then regenerates the electric signal based on this light. So the light source converts electrical into optical signals. So maybe 1 is a light pulse and 0 is not a light pulse. You see, this is modulation, because a light pulse typically consists of several of these waves, and no light pulse, nada, dark. We have the transmission medium, and the limiting factor typically is the detector. So because you have to convert what's coming in, your photons, you have to convert them into an electrical signal, then representing our ones and zeros again. Why does this work at all? That's physics again. It's the fact of total reflection of light at a change in the medium. And this depends on the so-called refractive index that also influences the speed of the light. But this indicates refraction effect relative to vacuum. What does it mean? We can have two media with medium 1 and medium 2 with different refractive index. Now, where do we have this? For example, you're here, that's a lake. Here, that's a lake, and you're here at the lake. And now, if you look on the water here, a bit further away, what you see is, oh, bright sky, because the light of the sky is reflected here. Total reflection of the light. You cannot look into the lake, so it's not possible to follow this line. So you see the reflection. If you have a close look here into the lake, then yes, you will see, for example, here the floor of the lake. But light does not follow a straight line, it will be bended here, depending on the incoming angle. That's basic physics from high school, and this is exactly used here now. Depending on the angle, you see these effects of the refraction. So if you change the angle, there's a certain point when suddenly light is reflected. And that's the idea, that we try to insert light into our fiber consisting of a certain medium with a higher refractive index compared to the surrounding medium with a lower refractive index, trying to keep the light inside this medium 1 in this example. So copper fiber, real one, looks like this. You see here our optical fiber. Optical fiber here, you see, consists of these tiny cores. That's the tiny one. Then there's cladding and plastic, etc. around it. There might be also some steel, whatever, aluminum core to make it more robust, because you may break the glass. You can also make this not out of glass, but plastic. This also works a bit cheaper, but not for long distances. So you have this core, optical glass, extremely thin. You can break this. Again, bending radius, important also for fiber optics. And you have all this protection, but important, the transmission takes place in the core of the cable with this high refractive index, and you try to keep the light inside the core, and you have always these reflections here. So that's the idea here. Okay, with all the reflections, and the index is then depending on the material, and we take many of them. So, how does it work? What are the differences of optical fibers? Shown here is, well, we have to get used to this way of displaying the refractive index. Is okay, on the y-axis the thickness of the core and the cladding. On the x-axis, you see here the refractive index. So this tells you this diagram, in the core we have a higher refractive index compared to the medium 2 was in the example, the cladding, the material around. So that's the idea, and the most, I would say, capable, also most expensive type of a fiber is called a single mode fiber or monomode fiber. This fiber has a very, very, very tiny core, 8 to 10 micrometers. And the idea is, if we now shine the light onto this fiber, all the rays can only take one single way. So it's very, very tiny core. And there's almost no reflection like this because the core is so small. And so all the rays follow one way, one path, and single mode, this name means that all waves take the same way, trying to prevent dispersion. We will see what the effects of dispersion is again. I introduced dispersion already, then we'll come back with the next type of fibers. It's a bit more expensive because we have a very small core, but monomode or single mode fibers are used to interconnect cities, continents, etc. But the manufacturing is a bit more expensive. This is why there's also a simpler so-called multimode fiber with a step index. Why step index? Because the index change is here indicated by this step. So we suddenly change from a lower to a higher refractive index exactly here at this border. Core diameter here is 50 micrometer, so it's simpler to manufacture because 50 compared to 8 or whatever, or even smaller. Okay, and the problem here is that, okay, we can now send one wave through this fiber, but depending on this angle, we also may have this modes, different paths, or we maybe also have this direct way going through the fiber, just example, simplified, etc. Or we even have an extreme case of a lot of reflections. And as you can imagine, if you are reflected many, many, many times, you need longer because the way is much longer compared to the straight line. So the ray that goes through this very straight mode is much faster on the receiver side. So what happens? You send a sharp pulse of light here into the fiber of a certain wavelength, and at the end this will smear out. You will see this effect of dispersion, because first this this single mode in the center will arrive, the signals, and then more reflected, and then maybe some of these extreme, often reflected signals will arrive on the receiver. So that's a problem. So you will smear this. And there's another problem. If you do so, imagine you send a sharp pulse and another one. This may result in first pulse is smeared over time, so dispersed. Next one as well. So that results in a overlapping here. Overlapping. And this overlapping may cause errors. And this limits the distance of different pulses. Because if the pulses come too close here together, you will have more and more overlapping pulses. So this is why you have to separate the pulses. And that lowers the data rate. So this is why monomode, single mode fiber can carry higher data rates compared to these very simple fibers. And there's a compromise where you actually use a fiber that can have different modes, so different paths, plus it has a larger core. But now the trick here is we have not a step index, but a gradient index. Gradient index here means so the refractive index changes slowly. What is the effect here? Well, you send over again your wave, but now waves traveling in the center are slower due to the higher refractive index, and waves traveling here closer to the next materials, they are, let's say, they are faster, so they can keep up. And this altogether squeezes together those signals, resulting in lower dispersion. So in the end, yes, we have different modes here. So you see, depending on the angle, how those waves arrive in the beginning of this fiber, because it's wider, 50 micrometers. But due to this gradient index, we can make it faster when we come to the edges, and so that in the end the dispersion is lower. So we do not really smear those pulses over a larger width. So that's the idea of this. And these gradient index multimode, these are the typical fibers you see in many, many places. Okay, different optical fibers, different characteristics. We also have to create our light, and there are different ways of creating, so radiation sources, and one is the classical one, LEDs, light emitting diodes. Very cheap, very reliable, so also when it comes to temperature variations, and so this is what you typically have in most consumer products. Capacity is not as high as lasers, but lasers, real lasers, are more expensive, sensitive, etc. So there are some pros and some cons for LED or lasers, and the advantage for laser is we can create a much smaller spectrum. That's a big advantage, and so lasers are then also better for dense wavelength division multiplexing, but more expensive. And also photon detectors, there are many different as well technologies how you can do this, and they all differ when it comes to the signal to noise ratio, because even if they do not receive any light, they might generate some current indicating there's something going on, and then there's a single photon arriving, and then they should really produce the current indicating that this was a logical one. But that's a science on its own. That's not the main topic of this course. So we can improve the materials, we can have better light sources, and so on. And if we all do this, we can come to this, and that's the keyword here, this dense wavelength division multiplexing. You can look this up in the internet, what you can do there today. To summarize, what are the challenges? Optical fibers, yoo-hoo, terabit per second, petabits, so that sounds good, but still we have attenuation, so the signal is weakened, so we have to regenerate the signal, so it's always weakened. So there, in the optical fiber, you have scattering effects, a bit of absorption effects, etc. So you weaken this, and you can impurities deflect individual rays. That's a problem. And you have some dispersion. So yes, this also limits the transmission range, as the rays of the light, well, they go through the medium with different speeds. So it depends on the mode. So and this depends on the angle of incidence. So how does light arrive here? A ray arrives here at our core, and is it reflected or does it go straight through our fiber? So that's one effect. So we have different speeds of the rays, and this causes this dispersion, this spreading of the signal. Then we have certain effects depending on the refractive index, which helps in our multimode fiber with gradient index. And in the end, you have to really optimize all these factors to avoid dispersion or to make the effect really small. So single mode fiber, that's a good idea because we only have the single mode. We don't have these multiple modes. So some questions for this. Fiber sounds perfect, petabits and terabits, so why don't we use fiber everywhere? Isn't this a good idea? So there might be reasons against it. Twisted pair is simple to install, everyone can do this, but you have to obey some things. So this is not a power line. And why twisting at all? Why is it called twisted pair? So why do we twist? We saw the advantages of single mode fiber. So, and what is this mode? What does it mean? And if you just look at your own installations, what type of cables do you typically see for your installation in your apartment, house, on the streets?